Hello everyone, today I'll be talking about ferrous hydroxide reduction, which is experiment 42 on page 341 in Schreiner's book. To start with, the purpose of performing this experiment is to check the presence of nitro group in the unknown organic compound we'll be testing on it. On the right side we can see how nitro group looks like. Nitrogen atom bonded to two oxygen atoms. To perform this experiment, we'll be needing two reagents. The first is ferrous sulfate reagent, and second is alcoholic potassium hydroxide reagent. And I'll be guiding through how to prepare these two reagents. First is ferrous sulfate reagent. We're going to weigh 5 grams of ferrous ammonium sulfate crystals, which has nice turquoise color. And we'll be adding these crystals into this 100 milliliters of recently boiled distilled water. So we're going to dissolve them. And then we're going to get a concentrated sulfuric acid. And using a dropper, we'll be adding around 0.4 milliliters onto the solution we have prepared. And then lastly, we're going to add an iron nail. Now, the reason why we add the iron nail and the sulfuric acid is to retard the air oxidation, which is the oxidation of iron 2 into iron 3, and we do not want that to happen. Second is the alcoholic potassium hydroxide. Similarly here, we're going to weigh 3 grams of potassium hydroxide, and then we're going to dissolve these into 30 milliliters of water to prepare a KOH solution. And then we're going to add this KOH solution into 100 milliliters of 95% ethanol. Then finally, that's it. We get this second reagent. Once we have prepared these two reagents, now we're going to need the controls. Our positive control will be a compound that contains a nitro group, such as nitrobenzene. And negative control will be those that do not contain a nitro group and is widely available in a regular organic lab, such as an ethanol. To check this positive control test, we'll be mixing the two reagents with the nitrobenzene according to a given step, and this given step will be the same step for the test on the unknown. And at the end, we should be seeing a red-brown precipitate, which is a ferric hydroxide. For a negative control, after we perform the same steps, we should be seeing a light green precipitate, which is ferrous hydroxide. The steps of the experiment will be the following. We're going to be adding 10 milligrams of the compound, the unknown, to 1 milliliters of ferrous sulfate reagent in a test tube. And then we're going to add 0.7 milliliters of alcoholic KOH reagent. Note that the order really doesn't matter according to the literature. However, it is advised to perform the experiment in the following steps, so that's because this ferrous hydroxide really quickly precipitates. Then we're going to insert a glass tube, and that it reaches the bottom of the test tube. And then we're going to pass a stream of inert gas through the tube for around 30 seconds. And the inert gas could be something like nitrogen. And the reason why we're doing so is to remove all the atmosphere, the oxygen inside it, and fill it with inert gas to prevent the oxidation due to the atmosphere, which is an unwanted oxidation. We're going to stop the tube quickly, and then we're going to be shaking it. And after 1 minute, we'll be noting the color of the precipitate. If there's a red-brown precipitate, then the unknown contains the nitro group. According to literature, the speed of the color change, which means the precipitation of the red-brown precipitates, depends on the solubility of the nitro compounds and the oxidizing power of the nitro compounds. For example, if we had aromatic nitro compounds, it tended to show color change much faster than aliphatic nitro compounds, and this is due to resonance effect that stabilizes the intermediate compounds during the redox reaction. The following table is taken from the literature, where we see a wide range of time taken for the color change, where the longest one was nitromethane, which took 60 seconds. That's why we need to wait at least 1 minute to note the color change. Now, if you see a light green precipitate, then the compound does not contain a nitro group, since no redox reaction has happened. And note that the green precipitates that we see can become slightly darker due to slight oxidation. And according to the literature, we see a wide range of the green precipitate color. It could be light green, it could be slightly dark green, it can be a gray green, yellow green, and there can be different shades of green. So if you see a different shade of green, you do not have to worry. The mechanism is the following. Once we mix the two reagents that we have prepared, which is the ferrous sulfate and the alcoholic KOH, what we'll see is a reaction between the two to form a ferrous hydroxide. And this ferrous hydroxide will be acting as a reducing agent in the presence of nitro group, thereby reducing the nitro groups into amino groups. And this is what actually happens. So when we have a nitro group, it's going to react with the iron 2, which is Fe2 plus, with a stoichiometric ratio of 1 to 6. So we're going to have 6 electrons being lost by the 6 Fe2 plus, and all of them will be going to the nitro group, and then we're going to have an amino group, and also we're going to have a ferric group, which is iron 3. And this iron 3 will form complex with its ligands, which is the 3 hydroxide groups. And this will cause the d orbitals of the Fe3 to split. And this allows the electronic transitions upon exposure to light, which leads to the red-brown color we observe in a positive test. Now, these are the references that we can refer to and which I have taken the tables from. Thank you.